going to explain the pH, decibel, and Richter scales as best as I can. The point of each of these scales is they deal with a wide variety of numbers. And it can quickly become very hard to plot those numbers, compare them, or understand how they interact with one another. I'll give you an example here. Let's say our numbers are decimal. We've got a couple of small numbers here. All right, and I want to be able to very quickly plot all of these numbers. And I got this tiny one there as well. So what you're going to find if you try and plot those numbers on any scale that you have, very quickly, you're going to find several of them indistinguishable. Let's say I take my largest number here, which is decimal 0.0015, and I make that my unit there. These much smaller numbers will essentially appear in exactly the same spot, making them indistinguishable and unable to plot. The solution that's used in chemistry, and that's for how acidic or basic a solution is, and they're looking at hydrogen ion concentrations, or in audio engineering when you're looking at sound levels that various sound sources produce, or in seismology, the Richter scale, where they're looking at the magnitude of earthquakes. In all three of those situations, you have these wide variety of numbers that need to be compared. And the way that's done is by taking the log of those numbers. And then they're modified in one way or another. For example, these real tiny numbers in the example of the pH scale, you take the negative of the log. That's what we'll do here. So looking at each of those numbers, so let's say that's A. Call those numbers A, B, C, D, and E. And I'm going to put these on a log scale. So if I find the negative of the log of A, so when we're considering number A, the negative log of 0.0001 is 4. For number B, the negative log of 0.000003 is 5.5. For C, the negative log of 0.00004 is 4.4. And for D, the negative log of 0.00015 is negative 3.8. Sorry, is positive 3.8. And finally for E, so this is the number that would be the hardest of all of those to fit on there. The negative log of 0.000000, I got 9 zeros there, 1, 2, 3, 4, 5, 6, 7, 8, 9 zeros before my 1. Is 10. Now let's look at all the numbers I have for plotting A, B, C, D, and E here. I now have 4, 5.5, 4.4, 3.8, and 10. This becomes very easy for me to plot, manage, and compare them. So I could plot them A, B, C, D, and E. My highest number here is 10. So that would be a 5 there. So A is a 4. B is a 5.5. C is a 4.4. So it's between those. D is 3.8. A bit below those. And then E is up here at 10. So it becomes very easy to compare each one of those numbers. They become quite manageable. Now, you have to understand the formula used to generate these numbers. In this case, because we're taking the negative, higher numbers correspond to a lower concentration, and lower numbers correspond to a higher concentration. This is done in the case of acids and bases. So in chemistry, you learned that with a pH value of 7, that's neutral. A low number is a very strong acid. And then a high number, and a high number on the pH scale is 14. That's a basic chemical. And by basic, I don't mean simple, I mean one that's an alkaline. So what we have is a scale where a low number represents a very high hydrogen ion concentration. So to have a value of 1, that means the negative of the log of the hydrogen ion concentration is equal to 1. And over here, the negative log of the hydrogen ion concentration is equal to 14. That would mean that the log of the hydrogen ion concentration is negative 14, which is a real tiny number. It would be 14 zeros after the decimal place before any significant digits. So for a pH value of a really low number, you've got a really high hydrogen ion concentration, and then a number up at 14, you've got a really low hydrogen ion concentration. And these really tiny numbers can be easily compared. Because you're taking a log, a change in one pH a change in a pH of 1 is a 10-fold increase. So for example, if you have a pH of 6 compared to a pH of 5, the pH of 5 has 10 times the H plus ion concentration of this one here, the pH of 6. So if you go down 1 pH, you have 10 times as much of a hydrogen ion concentration. If you have a change by 2, remember each time you change by 1 pH, you have a 10 times change in ion concentration. So a change in pH of 2 would be 10 times and then again multiply, because a log gives you an exponent, so this is repeated multiplication. So it's actually a 100 times ion concentration change. So with these really small numbers, by taking the log, they'll become negative numbers. Switching them to positive, we end up with numbers that can be easily compared to one another, plotted to one another, as long as you understand that whenever your pH drops by 1, that's 10 times the hydrogen ion concentration. So that's a pH scale. Let's look at the decibel scale now. So just as there's a wide variety of hydrogen ion concentrations that you have to consider when you're looking at acid and base reactions, when you're looking at sound intensity, there's this wide variety of sounds that can be heard. 0 decibel is the threshold of human hearing. Now, 0 decibel does not mean there's no sound. It is the quietest sound that an ear can detect just barely. Now, that's actually a little bit different for every human being, because as we get older, our hearing gets worse. But the threshold of human hearing is 0 decibel. So that turns out to be 10 to the negative 12 watts per meter squared. So if you study physics, you know that watts is a measure of power, and that's how much mechanical power is in the wave in the air per meter squared. If you have 10 to the minus 12 at 1,000 hertz, so that's 1,000 cycles per second, because the way we hear, our ability to hear changes depending on the frequency of sound. So there are higher pitches and lower pitches that you can and can't hear. Anyway, you don't have to worry about those details right now, but that's understood to be 0 decibels. Now that D in decibel means it takes 10 decibels for 1 bell, where 1 bell is a 10-fold magnitude change. So if your sound intensity is, let's say, I naught, so we use the word naught to indicate that 0. I naught is 10 to the minus 12. And then if we're looking for our decibel scale at I, so we've got let's say it is, I don't know, 10 to the minus 5. To convert that to a decibel, we multiply it by 10. That's what the decipart means. And that's 10 times the log of the intensity of sound we're considering divided by I naught. So as you can easily see, if the I value was also 10 to the minus 12, you'd be finding the log of 1. The log of 1 is 0. 0 decibels is 10 to the minus 12. So in this particular case, we've got the log of 10 to the minus 5 over 10 to the minus 12. So that's 10 to the minus 5. That's 10 to the minus 12. And when we divide them, we get 10,000. No, sorry, 10 million. Take the log of that. It gives us a 7. And then multiply it by 10 is going to give us a 70. So if you have a sound intensity of 10 to the minus 5, that is 70 decibels. So the decibel scale ranges typically from about 0 to 100. I mean, it can go higher for crazy loud sounds. Just to give you a bit of a reference here, if 0 decibel is the threshold of human hearing, so that goes from dead silence to hearing something but not being able to tell really what it is. Then 30 decibels is a whisper. 60 decibels is somebody talking. 80 decibels is somebody shouting. And 160 decibels if you've ever been to the air show, that's the sound of a jet engine. Every time you go up by 10 decibels, that's a 10-fold increase. So if you go up 20 decibels, that's not 20 though. If you go up 20, that's times 10 times 10, that's 100. So, for example, the intensity of sound of talking compared to whispering is a 30 decibel increase. A 30 decibel increase. We just look at how many times has it gone up by 10, and for each time it's gone up by 10, you multiply by 10. So that is a 1,000-time increase in intensity. How would you compare shouting to talking? Shouting is a 20 decibel increase. A 20 decibel increase is 100 times increase in intensity of sound. Okay, so let's say you have something that's at 100 decibels. And I want to know what's the sound intensity. Remember, your decibel value is 10 times the log of the intensity you're looking for over I naught, where I naught is 10 to the negative 12. So 100 decibels is 10 times the log of the sound intensity we're looking for over 10 to the minus 12. So do a little bit of math to that. Divide the 10s out, so you end up with 10 is the log of I over 10 to the minus 12. Now, how do we figure out what I is? If we're taking the log of it, we put this into exponential form. The exponential form here would be 10 to the 10 is equal to I over 10 to the minus 12. Okay, so I've just taken my log equation and converted it or rearranged it into exponential form. Watch the video on logs if you're not 100% clear on how to do this. Watch the introduction to logarithms if you don't understand how to do that. Now I'm going to multiply both sides, so I've got 10 to the 10 times 10 to the minus 12 is equal to I, which is 10 to the minus 2. 10 to the minus 2 is decimal 0.1. That's the intensity of sound of 100 decibels in watts per meter squared. Okay, so to recap, the point of these log scales, like the decibel scale, the pH scale, and I guess I don't want to make the video too long, I'm not going to go into detail, but the Richter scale works in a similar way. When you have widely varying numbers, you can make them more manageable by taking the log of those numbers. When you take the log of the number, it gives you essentially something related to the exponent when converted to scientific notation. By looking at those numbers, you can easily compare them, see which one's greater. And then in the back of your mind, you just got to make sure that you understand that every time you go up by a unit, it would be a 10-fold increase. You would take the previous value and multiply it by 10. Or if you go up by 2 units, it's not 20, it's 100. You multiply by 10 and then multiply by 10 again. It's repeated multiplication. The thing to remember for the decibel scale is inherent in it, it's 10 times the log. So you have to go up 10 decibels for a 10-fold increase, or 20 decibels for a 100-fold increase, or 30 decibels for a 1,000-fold increase. So each 10 decibels, you go times 10.